Morning. I'm Lanfa Liu. I'm from Technical University of Dresden. My supervisor is Zhuoru Li. And today my topic is about building damage mapping using very high resolution satellite images. First, I will talk about the motivation. So why we want to building damage caused by earthquake. Earthquake is one of the most devastating natural hazards, and it caused many people died and the loss of economic properties. And especially buildings are vulnerable to earthquake, and many buildings collapsed serious damage after the earthquake, like in 2008. Sichuan earthquake in China, 80% buildings of Sichuan country were destroyed, and in 2010 Haiti earthquake, about 300,000 buildings, residential or commercial buildings, were collapsed or seriously damaged. And also in 2015, Nepal earthquake, more than 250,000 buildings were damaged as reported. Actually, because of the buildings collapsed or serious damage, and many people died. So why we're using satellite images? Satellite images is obtained from sensors mounted on the satellite or maybe the aircraft. It can obtain information about a large area from a distance. It has been used widely in the natural hazards emergency response. It can be used in the vulnerability analysis, early warning, or damage assessment, and it plays a key role after the earthquake. So, in this project, we're using the deep learning or deep learning method. In this July, Microsoft announced a program about artificial intelligence for Earth. The aim is to address environmental problems using artificial intelligence. It includes agriculture, water, biodiversity, climate change. And I think natural hazards is also a very important area for artificial intelligence. By using AI, it can mitigate the impact of natural hazards and rescue people's life and reduce economic loss. So I personally append the natural hazards here, and maybe. Another reason is in this year's CVPI, there is a Earth Vision workshop. It focuses on large-scale computer vision for remote sensing imagery. By using computer vision or deep learning here, it provides a new way to see the information hidden in the satellite images. So next, I talk about the basic the workflow, how to collaborate the satellite images and deep learning to solve this problem. So first, we should prepare some data, and one of the most important data is the institute investigation data to know which building was damaged, and also the satellite images. if we have the image before the earthquake, it would be better, and as we can get a more accurate result later. So after preparing this data, the first step is to pre-process the satellite images to make the calibration, including the radiometric calibration, atmospheric calibration, and authenticated calibration. So maybe these are some remote sensing words. And after that, we should register this post-event and the pre-event images to make them perfectly overlaid. And then with this satellite images and the in situ investigation data, we can make a building map to know where is exactly the building located. And then by cropping or extracting the building patches, we can convert the problem into the traditional computer vision problem. Here, each building has like 100 by 100 pixels, and then next we can put the data into CNN. I will not talk about details about CNN, as I believe people sitting here and maybe know better than me about CNN. And then we can train the model and predict whether the building collapsed or not. As the building damage can be classified into 5 grades. Here, to simplify the problem, we reclassify the grades into 2 as non-destruction or destruction buildings. And finally, we can make a building damage map to help the local authority in rescue. So next, we talk about the case study about 2010 Haiti earthquake. It occurs on January 12, 2010, and have a moment magnitude of 7. And about 200,000 to 300,000 people died because of this earthquake, and many buildings collapsed or seriously damaged. So about the code, you can find the code in the GitHub. So here, this is the location of this case study. It's in the capital city of Haiti. Here, the red and the green one are the buildings. This data here are manually digitalized by ourselves, and we prepared about 2,000 building samples here. So as for the satellite images, the pre-image is obtained by the world view 1, and the post-earthquake we are using a QuickBird. Both images were provided by Digital Globe company. And the label data is collaborative work by several organizations after the earthquake. However, the label data have a problem that very few were groundly chosen. Before we here we also have to do some pre-processing about the dataset, as the buildings are in various shape and dimensions, maybe only a few pixels, or for some large buildings it can maybe several hundred pixels. So we should remove some of them and reclassify the data. So as for the method, after the reclassification, you can see that the data is imbalanced here. So we should consider some sampling method to balance the data. There are two major sampling methods. One is undersampling, and another one is oversampling. And here we're considering the one-sided selection, which is belongs to the undersampling method. It can select a representative subset from the majority class. So for CNN, we are using SqueezeNet, and if there are only the post-event images available, we can only use this dataset and train a model. If the pre-event images is available, we can directly make we can directly let the post-event image minus the pre-event images as the input data. SqueezeNet it contains a squeeze layer and an expand layer. With the same input and the output shape, it can reduce the number of parameters. So we are all as here if we have the pre-event and post-event images, we also consider it as a time series. Although the length of the time series is only 2, we can still try to test the performance of RNN. Here we for each image, for pre and post earthquake images, we can use the SqueezeNet by drop the last layer and concat them, and then you add a GRU layer here, and finally make a classification. The GRU is it has a similar performance compared to LSTM, but has fewer parameters. So let's see some results. First, we compare the models using different using the same data. Here, the same data means both the pre-event images and the post-event images. So by directly minus the pre-event images, here this one actually have the better results compared to the RN. Maybe RN is too complex for this problem. We also select several buildings here to see the probability of probability of these models. The first column is the probability of non-destruction, and the latter one is for destruction. So we can see I misclassified the second and the first one. And the next we compared the same model is different data sets. Here the first one is the same as before, using the SqueezeNet and the input data include the pre-event and post-event images. And the latter one is the SqueezeNet only use the post-earthquake images as the input data. And obviously, still the first one had the better result. And this is the probability of the selected buildings. So once the model is well trained, we can make a map about the earthquake area. So the first one is only contain the building footprints or building boundaries, and the red color and the yellow color means the misclassified ones, misclassified buildings, and we can also add the satellite image as the base map to make it looks better. And last but not least, I want to express the thanks to thanks to the Jeju campus for organizing and supporting this camp. And also, I'm using the Google Cloud computer engine and the TensorFlow. Thank you for your attention. Any questions?
Yeah, is there any question? Yeah.
My first question is, so if I understand it correctly, then did you use like the images, the 100 by 100 pixels to classify whether it's organized? So are you treating them as individual events and not considering that there are any neighboring structures? So like there might have been areas that are more densely damaged compared to others. So are you just treating them as individually and not taking account any geospatial information and such?
Here we only use the extracted building patches, didn't consider its neighboring situation. The geo information is not included here. Yeah, only the images.
And another question is there any particular reason why you use this SqueezeNet out of all models? Because as far as I know, it's only useful for like running it with lower parameters, and with your task setting up like so many parameters that it required to use that model in particular.
The main concern here is as the training data set is comparatively small, as it only has like 2,000 building images here. So maybe I think this model, as it requires less parameters, and it can be easily trained on this data set. Yeah, that's the main concern.
Thank you. And any other questions? Oh.
I have a question about your satellite image resolution, and if your model apply in the Jeju Island, how long takes time to simulation for this your model?
Sorry, I didn't mention the resolution of the satellite images. The satellite images have a resolution of half meter. And what do you mean by how long? How you mean to predict the building?
I want to know the area about if we simulate in the Jeju Island without earthquake, how long takes time to analyze the Jeju Island?
Here, the main problem is to prepare the data set. Actually, if you follow this workflow, you have to prepare the building map. If you already have one, then it's easy and it won't take much time. But if you have to manually digitalize these buildings, and it will take a long time. And for these 2,000 buildings, it takes maybe for one person maybe several days, 2 or 3 days to make the building map. But once you have all these data sets to train the model and to make the map, it can be done very soon. Yeah.
Thank you.
Is there any question?
Okay, thank you.